In this video I'm going to take a look at something called mass spectrometry and how we use the results from that to calculate the relative atomic mass. So in other words, using lithium as an example, where does this 6.9 come from? So the first thing we need to say is that almost all elements exist as isotopes. So what's an isotope? An isotope is an atom of the same element, so we've got the same number of protons, but they've got different numbers of neutrons. So there's a really simple representation of a typical element. This one I've given two isotopes, the blue squares and the red triangles. So they'll have the same number of protons, but they'll have different numbers of neutrons. And what that's going to do is it's going to give them slightly different masses. So basically all relative atomic mass is a measure of the mass of a typical atom in a sample of an element. So it's going to need to take into account the contribution, the mass contribution each isotope is going to have on the average mass of that typical atom. And we give that a special name. It's called a weighted mean mass. So the relative atomic mass is a weighted mean mass of an atom. So the next thing we'll do is just quickly look at mass spectrometry. So this is the technique used to find out what the relative atomic mass of an atom is. Very, very basic overview. I'm not going to go into a massive amount of detail because all I want to do is get to a point where you can see what a typical set of results looks like, and then how do you do the calculation to get the relative atomic mass. Okay, so basically a mass spectrometer is just this tube. It's got a curve in it, and the first thing they do is they'll take a gaseous sample of the atom in question. So my example here is going to stick with lithium, so it ties in with that first slide. We need it to be gaseous so that the particles can move through the spectrometer. So there's my gaseous sample of lithium. You can see there's two isotopes, lithium-6, lithium-7. Remember, they've got the same number of protons, just lithium-7's got one more neutron than lithium-6. Okay, so the next thing they do is they ionize, the atoms get ionized. You'll notice now we've got a 1+ charge there. The mass is still the same, we've just got a 1+ charge there. So I'll just quickly explain how they do that. So that's my representation for one of the isotopes. And what happens is it's fired with a beam of electrons, and the whole purpose of that is that the beam of electrons knocks out one electron from this gaseous atom. And what's that going to do? It's going to generate a 1+ ion, and there's the electron that's been knocked out of the atom. Okay, so as an equation, it would look like that. So the next thing to happen is the ions get accelerated. So they've moved from here to here. And the next thing they're going to do is going to hit this bend in the tube, in the spectrometer. So what happens when they hit the bend? They get deflected. In other words, they sort of separate out from each other. So you'll notice now that the ions I've deliberately sort of left some space between the two. So the lithium-6 is a lighter one. That's taken that sort of inside line, whereas the lithium-7, the slightly heavier isotope, has taken the outside line. And then all that happens next is they hit the detector and they generate a tiny electrical current. And the current's proportional. I'll refer back to this in a bit, but the current that's generated is proportional to the amount of that particular isotope. So if there was more of the 7 isotope, that would generate a higher current than the less abundant isotope. But I'll explain that again in a second. And then the final thing to happen is a spectrum is generated. So that's what we would look at, that's what we would see, and the spectrum would look something like that. So there's everything on one slide. So remember, the gaseous sample entered at the start. They then got ionized, so they turned into 1+ ions. They then were accelerated up this part of the spectrometer. They then hit the bend and they get deflected, and they spread out now, and then they hit the detector and they generate a tiny current that's proportional to the amount of the particular isotope in the sample, and that generates a spectrum. Okay, so what we're going to do now is take a closer look at the spectrum. So the first thing we can see is there's two lines. So what does two lines mean? What do the number of lines tell us? It tells us how many isotopes we've got. You'll also see that the lines have different heights. You can see that the 7 line is much taller than the 6 line. That's basically telling us that there's more of the 7 isotope in the sample than the 6. Next little thing we'll look at is this x-axis label. So you can see it says M over Z there. So what's the spectrometer actually measuring? It's measuring the mass of the isotope, so M, and it's dividing it by the charge of the isotope. So this is sometimes referred to as the mass to charge ratio, or you can just refer to it as M over Z. Now it's probably a good thing to do at this point to just go back to that slide where we looked at how the ion was generated. So remember, it was fired within a beam of electrons. That generates the 1 plus ion. Now if you think about the mass of your particles, the mass of an electron is almost 0. So the only difference between the atom and the 1 plus ion is 1 electron. So these are going to have effectively the same mass. So the mass of this is the same as the mass of the atom. So in the case of lithium, we can say that the mass of that is 6, and so is that. So if we think about the mass to charge ratio, M divided by Z, mass divided by charge, we're dividing the mass, 6 in this case, by 1 plus. So if we divide them by 1, we've still got 6. So the mass of this, the M over Z ratio of this, is the same as the mass of the atom. So we've looked at the x-axis. We'll have a quick look at the y-axis now. So you can see it says percentage abundance, and you'll notice numbers have appeared on top of the lines. Basically, the spectrometer can compare the relative amounts of the two, in this case, 2 isotopes. So you can see here as a percentage, we've got 7.41% of isotope 6 to 92.59% of isotope 7. So I hope that's made sense so far. What we can do now is have a look at a typical calculation. So remember at the start of the video I said that all the relative atomic mass is a weighted mean mass. So how do we use these results to get to that? So basically all we're going to do is we're going to take the percentage abundance and multiply it by the M over Z value. And then we're going to add that to the percentage abundance of that one multiplied by its M over Z value. Now we would stop in that case for this one because there's only 2 isotopes. If there was a third one, we would just add the percentage abundance times the other M over Z value. Because these are percentages, we're going to divide all of that by 100. So in this case, we're going to have the relative atomic mass is going to be equal, so we'll open a bracket, 7.41 multiplied by 6 plus 92.59 multiplied by 7, close brackets, all over 100. And then that comes out at a calculator value of 6.9259. So remember at the start of the slides, at the start of the video, I said where does that 6.9 come from? So at the 1 decimal place, that is 6.9. So in terms of a mathematical formula, all we've done there is to calculate the relative atomic mass, we've taken the sum of, that's what this symbol means, the sum of the percentage abundance multiplied by its isotopic mass, or M over Z value. So we've added all those together and divided by 100. So we're almost finished. We're just going to do a very similar calculation, but you'll notice that the y-axis is slightly changed on the spectrum. It's still the one for lithium, but you'll notice now instead of percentage abundance, it says relative abundance, and we don't have percentages here. We've got actual abundance values. So if you think about it, there's a total of 108 atoms in this sample. So 8 of them were isotope 6, 100 of them were isotope 7. So in terms of the calculation, it's virtually identical to the one you've just seen. So we still take the abundance number, multiply it by the M over Z value, and then add that to the next combination. But instead of dividing by 100, we divide by the total abundance. So in this example, we're going to divide by 108. So there's the numbers there, and the answer, of course, is going to be exactly the same, 6.924 0.59 or 6.9 to 1 decimal place. And in terms of the mathematical formula, relative atomic mass is the sum of the relative abundance now, not the percentage abundance, but the relative abundance multiplied by the isotopic mass, or m over z value, divided by the total of the relative abundances, not 100.